Hi guys, welcome to yet another interesting presentation of simulation for minerals industry. I hope you are enjoying the training and you have so far enjoyed the presentations that our team has delivered to you. So in this session, we are going to I'm going to show you the two types of simulations, dynamic and the steady state simulations. So let's dive into our slides. So we're going to talk about the two types of simulation, steady state simulation and dynamic simulations. I'm going to define to you the two types of simulations and their differences, and I'm going to show you where these types of simulations are best applied, and we're going to discuss where you think these two types of simulations are essential in your operations. So basically, we've got two types of simulations. We've got steady state simulation, which is also known as static simulation, and we've got dynamic simulation. These two types of simulation you have to know, or it's a must to know, because whenever you are building a simulation, you should be able to know what type of simulation you are building. Are you building a steady state simulation or you are building a dynamic simulation? So let us first look at steady state simulations. What are they? I think you have heard about the steady state simulators, but let us look at what steady state simulation is. So steady state simulation is a type of simulation which is used to simulate steady state processes or static processes or stationary processes. Steady state simulations, they are based on the laws of conservation of mass and on the laws of conservation of energy. That we talk about mass and energy balances. So this type of simulation does not have a time dependence. It does not depend on time in the sense that the variables, they don't change with time. So let us look at how a steady state simulator function. Steady state simulator functions by having information which is needed for plant feed and having information which is needed for plant design. These two, the plant design, the plant feed, and also what we call models. I think you remember from our first presentation when we talked about modeling and simulation, whereby I told you about how models are best defined. I think you still remember when we're talking about digital twins. So in a steady state simulator, there are models which are embedded in that type of simulator. And these models, they represent pieces or unit operations which are needed for building a flow sheet of the whole process. So these models, they are embedded in a simulator, and for the simulator to give you output in the sense of plant performance, in the sense of plant economics, it needs information about the plant design and about the plant feed. And this information works hand in hand with the models which are embedded in the simulator. And as an output, the simulator gives you a reflection of plant performance and as well as the plant economics, like plant operating cost, estimations of plant operating cost, and also estimation of plant capital cost. This is another representation of how a steady state simulator functions. So we talk about input, we talk about outputs, we talk about parameters which are fed inside a model, and the models, they build up to form a flow sheet in a steady state simulator. We've got different models. We can have a model of a cyclone, we can have a model of a ball mill, we can have a model of of a, let's say, a grizzly, a model of even material handling equipment like conveyors. So all this information is fed inside a simulator, and this steady state simulator composed of different equipment models. And from this simulator, we can have estimation of plant operation cost, plant capital cost, and even changes in and even parameters or model parameters or equipment configurations. And let's talk about dynamic simulation. Dynamic simulation is defined as an extension of steady-state process simulations. It is time-dependent and is built into the models via derivative terms. That is, there is accumulation of mass and energy. So it is different from steady-state simulation in the sense that the mass and energy balances, they vary with time. In steady-state simulation, there is no variance in variables. There is no variance in mass and energy balances. But in a dynamic simulation, there is variations. There is time dependence of mass and energy balances, right? So dynamic simulation also includes the description of startup and shutting down a plant, or changes of conditions during a reaction, or hold-ups, thermal changes, and more. Dynamic simulations are require increased calculation time and are mathematically more complex than a steady state simulation. So you'll find that when you are running a dynamic simulation, you can run a dynamic simulation over a long period of time, depending on the process, or over let's say there is a range in time of running a simulation, a dynamic simulation, as compared to running a steady state simulation. In the sense that for a steady state simulator, it's only dealing with one alteration, or you are just running the simulation once. You don't need to know how the variables depend with time. But with the dynamic simulation, you need time to run the simulation so that you can collect data which you can use to predict the behavior of a system. So dynamic models in nature, they take time to run. You can run a dynamic simulator to represent maybe a period of a year when your plant is operating, right? So dynamic simulations, they can be uh, described in online or offline fashion. Online in the sense that real-time simulation results can be obtained from a dynamic simulation. Let's say you are running your plant. At the same time you are running the plant, the dynamic simulator is also running and giving you results in real time. In the offline fashion, in the sense that there is no real-time collection of simulation results. The simulation model or the dynamic model can just be used to design, to troubleshoot, and to optimize the process. Or when you are conducting your case studies to assess the impacts of process modifications. So I want to highlight to you that dynamic simulations, they can be applied when one, you have got your real physical plant which is in place, which is already running. Two, when you have got a plant which is in the building stage or in the construction phase. So in the first case scenario, when you have got a physical plant which is already running, you want to apply dynamic simulation maybe for the cases of enhancing your control, and also collecting real-time data to see if to predict your system behavior with time. Scenario number two, when you are building a new plant, you would want to virtually commission your design before building a physical plant, in the sense that maybe after applying steady state simulation in the initial stages of the design, you then go a step further to enhance that steady state simulation to come up with a dynamic simulation which gives you a prediction of how your system that you want to construct will behave with time, right? And I think we've talked about the use of dynamic simulation in operator training. So sometimes maybe before commissioning, you would like to train your operators. So you can use dynamic simulation to train your operators. So someone can ask, how do I validate if this is a correct representation of the physical phenomena or the physical plant, whether I'm dealing with a steady state or a dynamic simulation. To validate a steady state model, you need sufficient plant data to gain insight into the average plant response, in the sense that for you to validate or to find if that steady state model, which is based on mass and energy balances, is a correct representation of the physical plant that you want to construct, or that design that you want to construct. So there is need for data, sufficient plant data to validate that model. The process of validating is just a it's in the sense that you want to find if this model that you have made represents or is useful to the task that it is intended to perform. Is it representing the physical plant? Can we rely on this model? So for you to validate a steady state model, you need sufficient plant data. So having said that, I want you to discuss with your colleagues in groups, in the chat group, in which areas do you think you can best apply steady state simulation and dynamic simulation models? So I want you to interact and have and brainstorm the areas that you think in your operation you can apply steady state and dynamic simulations. So with that, ladies and gentlemen, we've come to the end of this presentation, steady state and dynamic simulation. I will catch up with you in the next presentation. Thank you.